will start chapter 5. We're going to talk about sequences, series, and another method of proving, which we call induction. So our objectives is to learn about sequences, series, and induction. Okay, perfect. What is a sequence? Definition of a sequence. A sequence is a function with domain n. A sequence, a sub n, is a function, a sub n, with domain n. So it takes elements from n natural number set and maps them to R. When we graph a sequence, the graph is discontinuous or discrete. Of a sequence is discontinuous. And we can find the behavior, understand the behavior of sequence by taking the limit of that sequence while n goes to infinity. If this limit is equal to a fixed number, unique number like L, we say that we have a convergent sequence. Otherwise, we have a divergent sequence. We list the terms of this sequence as a sub 1, comma, a sub 2, comma, a sub 3, comma, and the rest of them. Then we add the terms of a sequence and we define something that we call a series. Definition of series. By adding the terms of a sequence, we form a new mathematical object, which is called a series. Okay, so the summation notation, Greek letter, sigma, the sum over the terms of the sequence, an, and starts from 1, goes to infinity. So here you have the summation notation, which is sigma. You read it as sigma. The meaning of that is addition or summation. So what does it give us? It gives us the sum, the addition of terms of the sequence. A sub 1 plus, a sub 2 plus, a sub 3 plus, and the rest of them. Very well. In calculus, you saw many sequences, many series. For example, remember you learned about harmonic series, which came from the sequence 1 over n. The sum 1 over n, and starts from 1, goes to infinity, 1 over 1, plus 1 over 2, plus 1 over 3, plus 1 over 4. We are adding the terms here, and here, this is 1 over n. If you list the terms of this sequence, it's going to be 1, comma, remember that this sequence is a convergent sequence because the limit of 1 over n while n goes to infinity is equal to 0, so it is convergent. But harmonic series is a divergent series. By adding the terms of this sequence, if we got this series, it goes to infinity. So divergent. Divergent series, convergent sequence, but we have a divergent series. So today we're going to talk about induction, one of the methods to prove some nice statements. So method of induction. In this method, you always have a statement involving n as a natural number, or sometimes you end up with some negative values and integers. So let Pn be a statement. I'm going to write down one example here at the same time that I'm writing this method for you. Example. Prove that 1 plus 2 plus 3 plus dot 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 plus n is equal to n times n plus 1 divided by 2. So method of induction, let Pn be a statement. In this example, your Pn is the whole equality here. So this is Pn. 1 plus 2 plus 3 plus n is equal to n plus 1 divided by 2. So to prove by induction, we assume the base step is true. Base step. P of 1. If n belongs to the domain of natural numbers, it always starts from 1. If the question says, hey, your n is greater than equals to 2, your n is greater than equals to 3, you have to check P of 2 or P of 3. So be careful, what is your beginning number? So in general, we say that, hey, our base step is P of 1. P of 1 is true. You need to check that P of 1 is true. So let's check that P of 1 is true or not. So you write base step P of 1. What's the meaning of that? It means that wherever I have n is equal to 1. Okay, on the left hand side, I have 1. On the right hand side, I have 1 times 2 divided by 2, which is equal to 1. So left hand side and right hand side are equal to each other, and you say that, hey, the base step is true. So you start with a statement, Pn. Your very first step is base step, P of 1. You have to check to see if left hand side is equal to right hand side or not. Our left hand side, n is equal to 1, so n is 1. We don't have 2, we don't have 3. It starts at 1. And right hand side, we just plug in 1 into the quantity here. We have 1 times 1 plus 1, 2 divided by 2. If you simplify this, 1 is equal to 1. So your base step is true. Then we start inductive step. Inductive step says if Pk is true, then pk plus 1 is true. So base step is easy. We're not so worried about base step. Inductive step is the step that is important for us. We say that if pk is true, what is k? K is a natural number less than or equals to n. If pk is true, then pk plus 1 is true. So this is the method of induction. So let us go to inductive step for this example. Inductive step. Inductive step says pk is true. pk is true. What's the meaning of that? It means that assume the statement is true for k less than or equals to n. So if I add 1, 2, 3 up to k, it is equal to k times k plus 1 divided by 2. Then we need to show that pk plus 1 is true. Okay, what does it mean? It means that I need to show that 1 plus 2 plus 3 plus k plus 1 is equal to k plus 1 times k plus 1 divided by 2. If I show this, then I prove that for the whole statement Pn. How do I show that? I want to show that. I know that 1 plus 2 plus 3 plus k is equal to k plus 1 divided by 2. I want to show that 1 plus 2 plus 3 plus k plus 1, this is p of k plus 1. This is p of k plus 1. So my last term is k plus 1. After k, you get k plus 1. 1 plus 2 plus 3 plus k plus 1 is equal to k plus 1 times k plus 1 plus 1. So you get k plus 1 plus 1 divided by 2. How do we show that? We have different methods. You can say that, hey, I already know that this sum is equal to this fraction here. I'm going to substitute that here. Substitute this guy here. Okay, what do we get? If I just write down k times k plus 1 divided by 2, here I get this. I get k times k plus 1 divided by 2 plus k plus 1. This is easy to work with. I just need to take common denominator. The common denominator between these two is equal to 2. So I get k plus 1 plus 2 times k plus 1. So let me just write a little bit further here. I need more space. Equals to 2 k plus 1 plus 2 times k plus 1. Take the common denominator. Okay. Here I'm going to factor out k plus 1, which is equal to k plus 1 times k plus 2 divided by 2. So this is my left-hand side. Is it equal to the right-hand side? Of course. These two are equal. By the method of induction, we prove that this statement is always true. This is true. Very well. Our next theorem is the sum of geometric series. I'm going to show that this formula is proven using induction method. Theorem. Sum of geometric sequence. Okay, perfect. So let R be a real number and R is not 1. Then the sum I starts from 0 to n of R to I is equal to R raised to I plus 1 minus 1 divided by R minus 1. There you go. This is the formula that you memorized in elementary calculus. Today we're going to prove it. So proof by induction. By induction. So suppose this is your statement. P n. This is our statement. It says the sum of terms R to I is equal to R to I plus 1 minus 1 divided by R minus 1. By induction, our very first step is to check to see if base step is true or not. So here you have base step for P of 1. It means that n is equal to 1. Left hand side, right hand side. Are they equal to each other? Okay. So if n is equal to 1, I starts from 0 and it stops at 1. You get R to 0 plus R to the first power on the left hand side, and on the right hand side, here your I stops at 1. It is equal to R squared minus 1 divided by R minus 1, which is R minus 1, times R plus 1 divided by R minus 1, which is equal to R plus 1. R plus 1 is equal to R to the power 0 is 1, so you get 1 plus R equals to R plus 1. So our base step is true. Now let us move on to inductive step. Inductive step says, suppose PK is true, we need to prove PK plus 1. So what's the meaning of PK? PK, it means that if I plug in K for n, I have this relation. I have R to 0 plus R to the first plus R to the K. If I add all of these together, it is equal to R raised to K plus 1 minus 1 divided by R minus 1. I know this is true. I'm going to prove that, so this is my goal. I'm going to prove that R to the power 0 plus R to the first power plus R to the K plus R to K plus 1. I'm going to use a different color for K plus 1, so you know that we are working with the inductive step. K plus 1 is equal to, I'm going to show that this guy is equal to R raised to K plus 1 plus 1, K plus 1 plus 1 minus 1 divided by r minus 1. We want to show that the left-hand side is equal to right-hand side. Well, you might say, hey, from pk, I know that the sum of r to the power 0 plus r to the first plus r to the k is already equal to this rational expression. So let us use it. Let us use it here. There you go. So this sum is equal to r raised to k plus 1 minus 1 divided by r minus 1 plus, now I'm going to copy down r raised to k plus 1 here, and I'm trying to simplify that. Let's take common denominator. This is equal to r to power k plus 1 minus 1 plus r to power k plus 1 times, inside parentheses, you get r minus 1. The whole thing is divided by r minus 1. Well, I'm going to distribute this by here. I get r to k plus 1 minus 1 plus r to k plus 2 minus r to k plus 1 divided by r minus 1. Here I can cancel out r to k plus 1, r to k plus 1. What's left? This is left. R raised to k plus 2 minus 1 divided by r minus 1, which is the same as this, equal to each other. So since they are equal to each other, we're done with this proof. Since pk plus 1 is true, we prove the theorem by induction. So here you have substitution. You can also use subtraction. Both of them are working here. One proposition. This proposition says, for all integers like n which are greater than equal to 0, 3 divides 2 to 2n minus 3. So what are we trying to prove? We're trying to prove that 3 is a factor of 2 to 2n minus 1. Well, let us use induction. Proof by induction. What is our very first step? Is the base step. Our base step says it must be true for p of 1. N is greater than or equal to 0, so I'm not going to use 1. Instead of 1, I'm going to switch it back to 0. It says n can start from 0. So remember that when we are trying to use induction method, we have to look at the domain that we have. In this case, the domain starts from 0. There you go. P of 0. It says show that 3 divides. So I'm going to put a question mark on top of this symbol, divisibility. Show that 3 divides 2 raised to 2 times 0 minus 1. So on the left-hand side, I have 2 raised to 0 minus 1, which is 1 minus 1, or 0, and we know that 3 divides 0. 0 can be written as 3 times 0. So now I say, hey, I don't need this question mark. 3 divides 0. And we're done. Okay. Now move on to next step, inductive step. Inductive step says, hey, if P of K is true, show that P of K plus 1 is true as well. Okay, we assume Pk is true. What's the meaning of that? It means that we assume that 3 is a factor of 2 to 2k minus 1. We assume this is true. We want to prove that 3 divides. So I'm going to put a question mark on top of it. 3 divides 2 to 2, 2 to k. 2 is in front of it, plus 1, minus 1. You need to prove this. Well, how do we prove this? Okay, I'm going to do a little bit of algebra and try to break this guy down a little bit. So, note that 2 to 2k plus 1 minus 1 is equal to 2k plus 2 minus 1. This guy can be written as 2 raised to 2 times 2 to 2k minus 1. I have 4 times 2 to 2k minus 1. Well, okay, take a look at this. Here you have 4. 4 can be written as 3 plus 1. This is equal to. So I'm going to use, so here I'm going to write it with a different color so you know what we did. 4. Now I'm going to write 4 as 3 plus 1 times 2 to 2k minus 1. I'm going to distribute 2 to 2k into parentheses. So what I get 3 times 2 to 2k, 3 times 2 to 2k, plus 2 to 2k minus 1. So let me write it here. To 2k plus 2 to 2k minus 1. Well, from this smiley face, from pk, I know that 3 divides 2 to 2. This is my pk. 3 divides 2 to 2k minus 1. At the same time, if you look at this term here, 3 is a factor here. So of course 3 divides 3 times 2 to 2k. 3 divides A, 3 divides B, 3 divides A plus B. Three divides the sum, which is equal to 2 to 2k minus 1.